Hi, in this video, we'll be talking about metric space topology. And so now we have come to the point where we want to formulate an idea that generalizes what we have in the real numbers, and in that we're talking about topology spaces already. And so in this part it gets a bit more abstract, but I'll try to keep it grounded by giving examples related to metric spaces, especially the Euclidean space of the real numbers. And so there's this notion about topology that we'll talk about in a future video. You can watch that first to understand this video, but in this video we don't need that as a prerequisite. And so we say that an open ball, we define an open ball at center x and radius r to be the set of all points in Rk such that the distance between y and x is less than r. In other words, you can imagine the space Rk here, or any metric space actually, and you have a ball centered around point P with the radius r. Then it's open if you don't include this boundary, and it's closed if you include it. A closed ball is one where you include the boundary, so the distance can equals to r. So you just collect all the points where the distance between x and p is less than r. And a closed ball is one where it can less than or equals to. And so this is the definition of open ball and closed ball. And now we say that a set is open with respect to the metric topology, meaning the dx, if and only for all points in the set there exists an r such that you can find a r radius ball containing p that's a subset of u. So what it means that u doesn't need to now look like a ball, so it can look like a very random shape, but you can find a ball at any small little ball at any point such that it's a subset of u. And now you can see why when it's open is defined to be this, because we don't need to consider the points along the boundary in the picture. Because along the boundary you can't find a ball such that it's a subset, but because you never hit the boundary, so that's how the notion of openness is formulated historically, I guess. But that's the intuition, and the definition is what we want to follow, is that for any point you can find a ball that's a subset of u. And a set is closed if and only if the complement is open. So take note of the difference. We are saying here is an open ball, and when you find a set, it doesn't need to look like a ball. But you can say it's open if you can find a ball at any point such that it's a subset of u. And we say a set is closed if the complement is open. So some examples of open sets in metric spaces are open balls. Of course, open balls you can again string the ball down to find a smaller ball such that the smaller ball is consumed within the larger ball. So you can just take this, you have random point here, you can find a smaller ball. And because open intervals are treated as open balls in the real numbers, open intervals in the real numbers are open. And so that's why they're really called open balls and open intervals. And with the notion of open sets now, we like to prove certain properties about them. And that for any collection of open sets, the arbitrary union of this family of open sets is open. And the arbitrary intersection of closed sets is closed. While the finite intersection of open sets is open, and the finite intersection of closed set is closed. Finite union of closed set is closed, I mean. And then this implies that the empty set and x are open in X. So we'll prove for the open case, as the closed case is just playing with set theoretic results and using the complements. And so for the open case, we'll start with the proof of A. So we are given a point in the union. We know that there will exist an alpha knot such that P is an element of one of the open sets. since this G alpha naught is open, there exists a ball that's a subset of G alpha naught, which then is a subset of the arbitrary union. And so this means that the arbitrary union is open because you can find a ball that is a subset of the larger set that we want. So this proves that the arbitrary union is open. And the proof of finite intersection follows because if we take a point P that is that's inside the finite intersection, then this point P is an element of G alpha for all alphas. So because G alpha is open for all alphas, for each G alpha there will exist a R alpha such that the radius R alpha ball is within G alpha. And then because it's finite, you can choose a minimum R, and it will show that the ball with this minimum R will be an element of all these G alphas, which then means it will be an element of the intersection. And hence, this proves that you can find a ball as a subset of the intersection, and so the intersection is open. And a classic counterexample to show why the finite intersection case needs to be finiteness is if you take the intersection of these open intervals, -1 over n to 1 over n, as n goes from 1 to infinity, then the only point it will contain is 0. And this is a singleton which is not open in R because it's not an open interval. And so you can see how later on we'll use this to actually develop our theory of topological spaces. And so now we want to talk more about continuity. And why do we establish this openness or introduce these open sets? Is because we want to have another notion, another equivalent characterization for continuity, and this is known as the open set criterion. It says that a map is continuous if and only if you take an open set in Y, you can find an open, then the pre-image is open. And really that's because of the definition of continuity, and we shall just reformulate the definition, the epsilon delta definition of continuity into writing it in open ball form first. So what does it mean? Because we are given an epsilon, there exists a delta such that when x is inside the delta, so when x is inside the ball of p comma delta, it implies that fx is an element of the ball fp comma epsilon. And so this means that the ball p comma delta is a subset of the pre-image of the epsilon ball center at fp. And so now we shall prove that if f is continuous, then if you take any open set V, because V is open, you can find a ball that contains it. And by continuity, it means you can find a delta ball that is open, that contains at P. And since this ball is already open, we just need to take all the P's in the pre-image, and this means that the pre-image is a union of open balls, and by the corollary that any union of open set is open, this means that this arbitrary union will be open, and hence this proves that the pre-image of V is open. Conversely, suppose that the pre-image is open for every open set V, then given an epsilon, we consider V to be the set of the open ball center at Fp, epsilon distance, radius. And this will be an open set. And so the pre-image will be open. And because this is open, you can find a ball such that P x is delta distance away from P. And because x is an element of this ball, fx will be an element of V, the pre-image of V, which means that fx is an element of V. And because fx is an element of V, it is fulfilling the epsilon, it is within the epsilon ball. And hence, this proves that the delta ball is a subset of the pre-image of the epsilon ball. And so we are done. I hope it's clear. You can rewatch the video again. But now you have another characterization for continuity using the ideas of open sets. And this definition is really what we use to generalize to topological spaces. And we'll talk more about that in future videos. So I hope you have enjoyed this video. I'll see you again. Bye.